Hello, my name is Abraham Ofori, and in this video, I'll take you through some limit exams practice questions. Okay, please subscribe to my channel if you haven't, share, like, and also comment for more videos. Okay, let's start. So, the first question that we are supposed to solve is this one: find the value of the limit as s approaches infinity of this expression 3 s squared plus 7x minus 1 all over the expression s squared plus 5. Okay, so when you have such a question and you are supposed to solve this with an idea and knowledge we have in limits, how do you go about it? Okay, someone may choose to use L'Hopital's rule. It will work. It will actually work, since if I put infinity here, I'll get infinity over infinity. Okay, but let's try to use other formulas and see, or other method and see, in case when you meet the question and there is no way you can use L'Hopital, how do you manipulate it? Okay, so here I can see that the highest polynomial here is s squared. So I can either use partial fractions or what. I can also try to divide the whole of every expression in this by s squared. Okay, so if you do so, then this is actually equal to the whole of this limit is equal to dividing the term here. It's like dividing the whole of the numerator by s squared and dividing this by s squared. In other words, it's like multiplying the whole of the numerator by 1 over s squared, multiplying this one by 1 over s squared. So it's like 1 over s squared over 1 over s squared. Nothing has happened. Okay, and try to push the 1 over s squared through the numerator and 1 over s squared through the denominator. If that happened, then we get here 3s squared over s squared, which is the same as 3 times s squared over s squared plus 7 s squared, sorry, x over s squared minus 1 over s squared. Okay, then this s squared over s squared plus 5 over s squared. In other words, if I'm to factor 1 over s squared out here, I'll still get back s squared plus 5. If I factor 1 over s squared out here, I'll still get the numerator, where the 1 over s squared at the top will cancel the 1 over the s squared here. So in other words, we've not done anything to it. Okay, now this is our new expression, so this can be rewritten as this. Then looking at this, we can simply put our, how do you call it, this infinity in. Infinity is any larger number. Okay, so it's very large. Infinity means you have a very large number. So if I put, let's say, 7 over a very large number, you can punch this on your calculator and you see that this will be turning to 0. 1 over a very large number squared, this will also be turning to 0. And 5 over a very large number squared, that one to be approaching 0. So you can point, or you can try 5 over 200 million or 200,000 squared and you get 0. Like 7 over 200 million, you get 0, like that. Okay, so it means that after putting all my infinities in, I'll get this side. Let's continue. I'll get this side to be 3, this one to be 0 minus 0 over 1 plus 0, which gives me 3, right? You can also use L'Hopital's rule and try to check. If you use L'Hopital's rule, you get something like 6x plus 7 over what? 2x. Still, if I put infinity in, I'll get infinity over infinity. So I differentiate again, I'll get what? 12 over what? 12 over what? 2. Okay, is that correct? Because if I differentiate this, I get 6x plus 7. Then here will be what? 2x. If I differentiate again, I get 6. Yeah, I get 6 over 2. And 6 over 2 give me what? 3. So in other words, you can also use repeater, but I'm just showing you how you can manipulate your function to get it easier. Okay, let's continue. Second question is, find the value of the limit as s approaches 3 of this. Here, let's see if we can put 3 in straight and do away. Limit is something that, or somehow, limit is the functional value of all the s's as they approach 3. Okay, either from the right of 3 or from the left. So you can try putting some functional values here and see what you'll be getting. You will see that if I put, let's say, 3 here, I get 1 over 3 minus 1 over 3, which is 0. No problem here. But if I put 3 here, 1 over 3 minus 3, which is 1 over 0, and this we can do. Okay, so we have to continue, use any other method and see. Let's see what we can do with this. Okay, so with this, we can solve this fraction aspect first. Okay, and this is how it becomes. All right, after solving this fraction, this is what you get. Then you continue manipulating it. This 3 minus x here can be rewritten as what? Minus into bracket x minus 3. This is true. All over 3x. Okay, then it means this is the same question. I've not done anything to it. Then I can continue, and then x minus 3 can cancel x minus 3 here. You see that, right? And I'll be left with negative 1. Then I'll be left with negative 1 over 3x, since here is only 1. Then from here, I can put my 3 here, and I'll get 3 times 3, which is 9. And this becomes negative 1 over what? 9. Pretty cool, right? So it's very easy. Just that you have to think and know how to manipulate your question. Okay, let's move on to some difficult one and see. Find the value of the limit. So if I'm given this expression, square root of x plus 5 minus square root of x, I'm supposed to find the limit of this expression as x tends to infinity. How do I solve this problem? Okay, now the limit of this as x approaches infinity, I can rationalize this. I did a first video on, I have some video on rationalization of set. I said you can rationalize the numerator of a set, and also you can rationalize the denominator of a set. The reason why we are trying to rationalize is because we can't put infinity here and then we'll be able to go. No, you have to simplify it in such a way that when we put infinity here, we'll be fine, we'll be okay. Okay, all right. After rationalizing the numerator, this is what you get. Okay, rationalization of set, we said you just multiply both the numerator and the denominator of the fractional set with the conjugate of the part that you want to rationalize. Okay, so here we want to rationalize the numerator. This whole thing is a fraction of denominator, what? 1. So we want to rationalize the numerator. Then you find the conjugate of this, which is square root of x plus 5. The conjugate to be plus square root of x. Then I multiply this with both numerator and denominator, and this is what I have. Okay, continue this. You can see that this is difference of two squares. I pick one of them and square it, minus I pick the other one and square it, all over this, right? Then in this case, if you square this, you get s plus that. If you square this, you get x. Okay, I subtract this and this, and what will I get? I'll get something like this. This is 0 because here I get 5 over the expression square root of x plus 5 plus the expression square root. Right, now if I put infinity here, we are saying that infinity is a very large number. Okay, so if I put infinity in place of here, it will be infinity plus 5, which will still be a large number. And the square root of a very large number will also be what? A large number. Plus the square root of a large number, which will also be what? A large number. When I sum them, I'll still get another large number. So 5 over a very large number is 0. You can try that on your calculator by punching 5 over, let's say, square root of 1000 plus 5 plus square root of 1000. And I'm pretty sure that you get something that is closer, very closer to 0. And this, as you continue and take very large numbers, you eventually get 0. Okay, that is it. Let's move on. Find the value of the limit x multiplying the whole of this expression, square root of s squared plus 1 minus third root of s cubed plus 1. How do you solve this? All right, very interesting, right? You can think about this more and then we start. All right, solution. So this, I can push this x inside this. When I push it inside, it's like x times the square root of this. And this side, look at this side. S squared plus 1. I can factor s squared out from here. When I factor s squared out, what will I get here? I'll get 1. Here I'll get 1 over s squared because we want to write an expression that after we multiply this through, we get this back. Okay, let's try and see. S squared times 1, we get what? S squared. S squared times 1 over s squared. This s squared will cancel this and I'll get 1. So it means this expression here is the same as this. Okay. Now, this side too, we do the same by factoring x cube out. Okay, and get 1 plus 1 over s cube. Here, mind you, our x is here. This is just the third root of it. Okay. Alright, let's continue and see. Now, this x, the square root of this, if you remember, I've done a video on Z, how you can manipulate Z. The square root of a certain number times another number, something like, let's say, square root of AB is the same as the square root of A times square root of B. So here we apply the same principle here. Square root of s squared times this expression is the same as square root of s squared times the square root of the whole of this expression. And square root of s squared will give me what? X, or the absolute of x. Let me put it that way. And it becomes x times, there is another an original x here. Okay. Now this the same thing applies here. The cube root of a times times b is the same as the cube root of a times cube root of b. And here I can take the cube root of s cube, which is x. This is it. This is it. So this is it. Okay. Cube root of s cube, which is x. Then I have my original x here. I multiply it by that. Then the cube root of the whole of this expression. I hope this is okay, right? Now let's continue and see. I can remove the square root here. When I multiply this and this, I get what? S squared. When I multiply this and this, I get what? S squared. When I remove the square roots, if you remember in our set, we said any number to the power 1 over n is the nth root of it. But if I have the nth root of that number, I can take it back to the powers and say it is the number to the power 1 over n. So here, same thing applies here. The whole of this is the same as 1 plus 1 over s squared all to the power 1 over 2. The minus s squared into bracket 1 plus 1 over s cubed all to the power 1 over 3. Okay, so what do we see here? Still, if you put our infinity in, we still be getting some big problem here. Someone might say, why don't you put infinity in? Because there's a minus here. Infinity minus infinity will get 0. No, please. Because we don't know the actual infinity. We are saying that x is approaching a higher number. What if here the large number here is different from this one? Okay, so let's solve it, try to manipulate it again. But this expression here, okay, is of the form a certain number plus x all to the power n. Okay, and this we know it from binomial expansion that we can expand this as what? A to the power n plus n a to the power n minus 1 x plus n into bracket n minus 1 over 2 factorial a n to the power 2 minus a n to the power, it's a to the power n minus 2 s squared plus dot dot dot. You continue like that. Okay, so it means that I can expand this and I can also expand this and see what I will get. Okay, so if I take the first one, expanding it will give me a, which is the 1, plus nx, which the n is a plus na to the power what? N minus 1, right? And so n, this is the n, which is the power. A is what? 1. 1 to any power is what? 1. So that's why you didn't write the 1. Then it becomes x to the power what? 1. So it becomes our x here is 1 over s squared. So this to the power 1. And plus n minus 1. N is what? Half, which is 0.5 over 2 factorial. Then x to the power 2. Here our x is what? 1 over s squared. When you put 1 over s squared to another power 2, we get 1 squared over s squared, which is 1 over s to the power 4 plus dot dot dot, right? Now this can be rewritten as what? After simplifying this side, I'll get x squared. You know, in our previous this question, you have s squared multiplying this. So now if you've been able to expand this, then you multiply through by what? Our s squared. Okay, so s squared times this is the same as saying that s squared times the whole of this. Now if you multiply through, S squared times 1 will give me S squared. S squared times this. The S squared will cancel this S squared. I will get 1 over 2 minus S squared times the whole of this. I will get this. After simplifying, I'll get something like this. Then S squared times 1 over S to the power 4. From indices, the S squared will reduce this to what? S to the power 2 plus dot dot dot. Okay, so S squared will multiply a whole lot of them here. But mind you, the rest, since the power of x here, down here, is always bigger than S squared, okay, the rest will be having x to the power something um on the denominator, sorry, at the denominator level. Okay, that's why we didn't write. Now this to the power 32, this one too, we can expand it like this. Okay, now let's see something here. S squared times this, I'll get S squared. Because in a previous question, there's an also an S squared multiplying this one also. Okay, so sorry, S squared times this one, I'll get S squared. S squared times this, I'll get 1 over 3, which is 0.3333 times S squared, and S squared will reduce this to 1 and become 1 over x, and minus this one. When you simplify this, what you get, S squared times this, it will reduce this to what? S to the power 4 plus dot dot dot. So the rest will be reducing by x to the power 2, and we will still get x at the denominator. Okay, now this, there is an expression here in our question that was a subtraction, excessive subtraction between the whole of this and the whole of that. Now we know how, well, we know how we can write this. Okay, this, the whole of this is what? This one, and the whole of this S squared times that is this one. Now let's subtract them and see. So it's the whole of this minus the whole of that. Okay, S squared minus S squared, you get what? 0. That's why I didn't write anything here. Half, you don't have any half here, so I just write my half. Then this, I don't have a square here, so I get what? Minus 0.1251 over S squared. I write it plus dot dot dot. You see there's a plus dot 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 here. Minus the whole of this. Okay. Minus this is the same thing. So minus the whole of this. Because the reason why we didn't do is that we don't know the rest, but where we are interested in is this part. This, there's an S square here, there's an S square here. When they subtract, what will I get? I'll get 0. And I'll be left with these. So this is the final answer for the expansion of these. Okay, now let's go and take our limit. Oh, sorry, the limit of this is half. Let me explain it. I think I made a mistake. So okay, right, if we are taking the limit as s approaches infinity, it means wherever I see my x, I put infinity there. Okay, so 1 over x squared, that becomes 1 over what? Infinity squared, which will also be infinity. And we said any number to over infinity is what? 0. So here I'll get 0 for this side. Now there's an infinity here. 1 over infinity is still 0. There's another infinity here. So if you can see clearly from here, every term here again will have an x at the denominator, which would make limit tend to 0 whenever we put our infinity in. Okay, now the only part that will be left is what? The part that doesn't have any x. Okay, and that is half. After doing this, we will be left with only half, which is not having an x. Then this means that the limit as s approaches infinity of this, and you know that this whole expansion of this is the same as what? This one is equal to what? 1 over 2. This is pretty cool, right? So let's go and see other forms of limit and know how to solve them. Okay, now we have something that we call L'Hopital's rule. All right, in the L'Hopital's rule, when you are given a limit to find, you find the functional value of the limit at that point, and maybe you are getting something like 0 over 0 or infinity over infinity. Then you can apply what we call L'Hopital's rule. This, it means that for us to be able to use L'Hopital's rule, you're supposed to make sure that our function is what? A fraction. Okay, so let's see. The first example is we are supposed to find the limit of this. The reason why we are using L'Hopital's rule is that after manipulating this, you get something similar. So with this will become 0 to the power 0, and 0 to the power 0, as at now, you still don't know. Okay, you are saying, I don't know if you say it 1. After this limit, you will actually understand if it is 1 or not. Okay, so let's start and see. Now, we are letting our y to equal to the whole of this limit. So if I take my y to be the limit of x to the power x as s approaches infinity, then the length of my y is equal to length of the whole of this. And now, mind you, this limit is an operator. So the length cannot work on it. It has to push through the expansion or where the variables are and then work on it. Okay, so it becomes length of y is the same as limit as s approaches infinity, length of s to the power x. Now I continue, and length from logarithm, we know that logarithm of a to the power n is the same as n logarithm of a. Okay, so we apply the same thing here. Hence, still we are still in our length of y. Length of y is equal to the limit as s approaches infinity. Sorry, s approaches 0 of this one. Look at here. I just maintain my length of x, and I divided length of x by 1 over x. If you have time, you can solve this fraction and see what you get. After simplifying this, you still get back this. We want to make sure that we get something like something over something, and that will give us the opportunity to use what L'Hopital's rule. Okay, because without that, you can't solve this limit question. All right, let's see. If I put 0 in, okay, length of 0 is what? Infinity, right? Now 1 over 0 is what? Also infinity. So it means that you've gotten something like infinity over infinity, and then you apply L'Hopital's rule. L'Hopital's rule is saying that if you have a limit that when you find the functional value of the function at that point, say 0, and you have infinity over infinity, what you can do is just differentiate this and differentiate the down. So differentiate ln x, what do you get? You get 1 over x. If I differentiate the down part, I'll get negative 1 over s squared. Okay, now simplifying this fraction, it means I have 1 over x here, multiplying the reciprocal of this, which is that, and then this one of the x's will take this out, and I'll be left with what? Limit of x to the power what? 0. Sorry, as s approaches 0, negative x. Okay, so limit as s approaches 0 of what? Negative s. Still, ln of y is equal to that. Okay, then limit as s approaches 0 of negative x. I just put my 0 here, and I'll get 0. But yes, still, we've not solved our question, because the question is supposed to be simplify this one, not ln of y. Okay, so it means my y from indices, this is the same as logarithm of y to the base e. So if from the basic definition of logarithm, if I want to rewrite this as exponential form, then the base will come and carry this one, so it becomes e to the power 0, and this will maintain. So y equals e to the power 0, which is equal to what? 1. Okay, but what is our y? We said our y is what? Limit of x to the power x as s approaches 0. So it means that the limit of this as s approaches 0 is equal to 1. And indeed, any number to the power 0 is what? 1. Okay, this is very cool and clear. Okay, now let's continue. So we are supposed to find the value of the limit of as s approaches 0 of s cos s over s plus arc sine x. Arc sine is the same as what? The sine inverse of x. Okay, now since this won't work, because if I put 0 here, it becomes 0 cos 0, which will be 0, because cos 0 is 1, but 0 times any number is 0, and I get 0 plus sine inverse of 0 is 0. Okay, so this won't work, and then we get 0 over 0, which L'Hopital will also permit us to use his the idea. Okay, like I said, if you want to use L'Hopital's rule, once you've confirmed that indeed your functional value of the point is 0 over 0 or infinity over infinity, then you have to differentiate the top one and differentiate the down one to see if you can solve. Okay, so if I differentiate this side, I just keep cos s, then differentiate x, I'll get what? Cos x. So differential of x is 1, become 1 times cos s, which is cos s. then minus, I'll keep this x and I differentiate this. The reason why we are bringing minus is because it's supposed to be plus, but the differential of cos s is what? Minus sin s. Okay, this is very cool, right? Now all over the differential of this side. So in L'Hopital, we just differentiate the top alone. That is all. Differentiate the denominator alone. If I differentiate x, I'll get 1 plus differential of arc sine x, sine inverse of x, is equal to 1 over square root of 1 minus s squared. And if you don't know how to prove this, I've proved it in one of my videos. You can go and check it. Okay. Alright. Let's continue. Here, if I try to put 0 in, what will happen? Because 0 is what? 1. You can put it over a calculator and you get 1. Minus 0 times this will be 0. So it becomes 1 minus 0. Now, if I put 0 here, it becomes 1 minus 0, which is 0. And square root of 1 will be 1. So I'll be left with cos 0, I said is 1, minus 0 over 1 plus square root of, so 1 over square root of this. Now I said when you put 0 here, you get 0. So 1 minus 0 is 1. Square root of 1 is 1. So 1 over 1 plus 1. 1 over 1 is 1. So become 1 plus 1. And this will give me what? 1 over 2. Alright. This is very, very simple to understand. Now you're supposed to evaluate this. The limit as s approaches infinity of this. How do you go about this? Think about it, okay? This one too, it's not L'Hopital though, but I just wanted us to go through it, okay? Look, I want to manipulate this side. If I divide the whole of this by what? 1 over s, I still get this back. Because if you want to simplify this, the whole of this times the reciprocal of this, which is x, and I'll get this back. Alright, let's continue. If that is the case, okay, if that is the case, L'Hopital can work on this side, okay? Although L'Hopital, we are not seeing L'Hopital here because there is no infinity over infinity here or 0 over 0 here. But here L'Hopital can work because if I put infinity in, this becomes 2 to the power 1 over infinity, and we say 1 over infinity is what? 0, so it becomes 2 to the power 0 minus 1. 2 to the power 0 is what? 1 minus 1 is 0. Here, if I put infinity here, I'll get what? 0. 1 over any big number is 0, like I said. So it becomes 0 over 0, and that will permit us to use what? L'Hopital's rule. Let's continue. L'Hopital is saying that if I want to use his rule, I have to differentiate the top, which is what? Differential of a, an exponential function or an exponent. I have that one too video there. If you want to know how you prove it, you can go and watch. But you just write the same function back. Differentiate the top here, multiply by it. The differential of this is minus 1 over s squared. Then times length of the base here. Okay. That, but when you differentiate one, you get what? 0. So the differential of this alone is given as this. Now, the differential of the down here, this one, is you use quotient rule and you can get negative 1 over s squared. Okay. Now this is the same as this negative 1 over s squared can take this negative 1 over s squared out. Now I'll be left with what? Limit as s approaches infinity, 2 to the power 1 over x, ln of 2. There's the ln 2 here. If I continue simplifying, as s approaches infinity, 2 to the power 1 over 2, 1 over x is the same as 2 to the power 0, because here 1 over x, where x is a very huge number, is 0. Then 2 to the power 0 ln 2, which will give me what? Ln of 2. Okay. Now, we are done with the exam practice questions that we went through. I will bring another video on exam practice question on limit, and when that one too come, kindly go through it for you to be able to solve every limit question that you'll be given. Okay. Now note the following. If I have limit as s approaches infinity of any number a over x, this is equal to 0. Okay, this should be equal to 0. Alright, let's continue. Limit of sine x over x as s approaches 0. This L'Hopital will work. Sine 0 is 0, 0 is 0. Okay, can use L'Hopital and cross check this. This is equal to 1. But limit of cos x over x as s approaches x approaches 0 is infinity. Okay, so these are the things that I wanted you to know, note, and write them down, because you might meet them in our next tutorial video on how to solve exam practice questions. Okay, so thank you And please don't forget to subscribe to my channel and comment as well for more video. Okay, see you next time.